Hello friends, this video on Chemical Kinetics part 13 is brought to you by examfear.com. No more fear from exam. Now we'll talk about a new topic called integrated rate equation. See, we have seen that for a equation a plus b is equal to c plus d, my rate is nothing but k a to the power x b to the power y. These are experimental values. And rate is nothing but minus dr by dt. Right? It is nothing but k e to the power x b to the power y. Now, when I am doing an experiment, and let's suppose I have to find the value of k. So either I have to find the value, to do that I have to repeat this experiment so many times, and I have to find the concentration of A, concentration of B, and dr by dt also. Correct? But finding dr by dt is difficult using experiments. This is nothing but instantaneous value. Instantaneous rate. It's very difficult to find the instantaneous rate of reaction just by looking at the reaction. For that we have to plot the graph, and at the given point we have to find the tangents. Very difficult process. Right? For example, you do keep doing experiment, you get this graph of the reactant, and to find the dr by dt here, plot the graph, put a point, find a tangent, put a minus sign. Same thing here. It's a very difficult process. To avoid this, if you see, this is a integral equation, and we can use some maths. We have learned this kind of equation in the maths. We'll integrate this differential rate equation, right? And with this, we'll get a relationship between this concentration at different time and rate constant. So we'll show you this. We'll integrate these equations and we'll get a better equation, because finding dr by dt is difficult. When you're doing an experiment, at that time finding dr by dt at different point of time is difficult job. To avoid this, we'll integrate this whole equation and we'll get a better relationship. We'll do this for zeroth and first order only. Let's do this for zero order equation. So let's suppose this is a zero order reaction to product, right? So my rate here is nothing but minus dr by dt. That is nothing but k into reactant to the power 0, and that is nothing but k, because it is zero order equation. Correct? So I can have, end of the day, what I'm having is dr by dt is nothing but minus k. Correct? Or I can say dr is nothing but minus k dt. Let me integrate both sides. So what you get, dr integration you get r, minus k dt you will get minus kt, and some constant you will get integral constant I. And we need to find the value of I. To find the value of I, what we can do is we can put the value of r at different temperature, and we will get the value, because this is a constant, right? So let's see, at t is equal to 0, my concentration is what? R0. So let's put the value in this equation 1. R0 is equal to minus k into 0 plus I. So my I is nothing but R0, initial concentration. That is the value of I. So with this, my equation become R is equal to minus kt plus R0. Correct? If you see this equation, R is my concentration at any given point of time. It's a variable. Time is my variable. K is constant, R0 is constant. R0 is the initial concentration. This is almost similar to y is equal to mx plus c. That means in y, if I draw concentration, in x, if I draw time, x coordinate time, y coordinate, I'll get a straight line with a slope of minus k, right? And this is c. X intercept has to be, sorry, R naught, initial concentration. T is equal to 0, R is equal to R naught. And you see the concentration is decreasing over a period of time. This is for the zero order reactions. Please note, zero order reactions are very uncommon. Very uncommon. They occur generally in the presence of enzyme or special condition. Very few reactions. Some reactions are, for example, NH3, a very high temperature, and with catalyst it will decompose into nitrogen and hydrogen. Or in this case, rate is zero order. Or for example, Hi in the presence of gold will break into H2 and Hydrogen. This is also zero order, but there are very few zero order reactions in the real world. So this is the reaction we got. R is equal to minus Kt plus R naught. And if you plot the graph, if you compare this, y is equal to mx plus c, and y you put as concentration, x as time, then you'll get a graph like this with slope of minus k and initial this is R naught. If you see, as the time goes on, the concentration decreases, concentration of reactant decreases, and it goes down. Correct? Let's see for the first order reaction. So let's take the first order reaction. We have, let's suppose, some reactant and it forms some product. And this is first order reaction. So I'll say the rate is what? Minus dr by dt. And there is nothing but k into r to the power 1. With this I got what? dr by r is nothing but minus k dt. You integrate both sides. What you get is ln r is nothing but minus kt plus some integral constant. To find the value of integral constant, let's put that at t is equal to 0, r is nothing but r naught, initial concentration. We have seen this. This r is at any time. So let's put that in this equation 1. You get ln r naught is equal to minus k into t0 plus I. So I is nothing but ln r naught. Let's put the value. Ln r is equal to minus kt plus ln r naught. Correct? Or I can say that ln r by r naught is equal to minus kt. Now if you compare this equation with y is equal to mx, where x is my t and y is equal to ln r by r naught, you will get a straight line graph. If you plot this graph between ln r by r naught and t, what slope will be? Minus k. Right? We'll see this graph on the next page. So that is what you will get. Or the same equation, actually, the same equation, if I want, I can also write r is equal to r naught e to the power minus kt. Same equation. Removing ln from both sides, this becomes e to the power minus kt. R by r naught is equal to e to the power minus kt. So r is equal to r naught e to the power minus kt. Correct? This is ln. If you want to make it log, you can do that also. So this is the most common form of equation. This ln you can make it 2.303 log. This becomes 2.303 log r by r naught is equal to minus kt. That is also one form of equation. You can use any of these. or let me write it actually, because we use that equation pretty frequently. So ln becomes log 2.303 log, right? R by R naught becomes R naught by R, and here we get minus. Just flip it. Equal to minus kt. Why I am doing this? Because I want to get rid of this minus sign. Or k becomes 2.303 by t log of R naught by R. This is something which we'll use very frequently. But for the graph, we'll use this equation. But the same actually, instead of ln I made it log, and I just removed the minus sign by switching this R by R naught to R naught by R. Okay, now let's plot the graph. So the equation which we had was ln R by R naught is equal to minus kt. Correct. If you see, compare this with y is equal to mx, slope is minus k, slope is minus k, right? And this becomes y, ln R by R naught, and t becomes x. You get this kind of graph. Correct. So examples of first order equation. A lot of reactions are first order actually. Hydrogenation of ethane, or ethene. We get ethane here. This is first order equation. So here rate is equal to k into C2H4 to the power 1. In fact, if you see, all the natural and artificial radioactive decay of unstable nuclei is first order equation. For example, 226 Ra will give you a helium plus 222 86. The rate, if you see, is nothing but K concentration of Ra to the power 1. So all the radioactive decay is generally first order equation, right? Also, if you see the decomposition of N2O5, N2, these are also my first order equation. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.